This project is in the fifth phase. As you can see, it's a continuous effort of iNEMI to address the package warpage challenges. In the earlier phases, we worked on package warpage characterization, about the metrology, the trend of the package warpage of different package types. Since last phase, the phase 4, we start looking into the warpage prediction, the modeling and simulation. So for phase 5, we did further work based on the gap identified in the phase 4, trying to work on the framework on the package warpage prediction. And we work with different companies. We have Kang Yu on from Intel. He's chairing this project. Kang Yu is a senior assembly and packaging analyst at Intel, focusing on the mechanic and assembly technology challenges. So with that, I will pass over to Kang Yu to go through the presentation and introduce what we have done with the project and some learning, some results. Okay, Kang Yu, go ahead.
Yep. Okay. Thank you, Haley, for the short introduction. And good morning and good evening to everyone. So today I'm here to present about the phase 5 project summary for package warpage prediction and the characterization. So before I start, I would like to thank the member here for their participation and contribution in this project, especially Shrinkage for their sample and raw material donation. So to Econometric and Institute for their support on the experiment measurement and data analysis, and also the support from Model 3D and SIS, ISAC-M for modeling approach and analysis idea. A big thank you to you all for your contribution. Okay. So some background about this project. It is about research and study of dynamic warpage characteristic of our latest packaging technology and warpage measurement methodology. Phase 5 project is more focused on the modeling framework from the model generation, material property, and the simulation capability to predict the package warpage. For material property characterization, it involves PVTC or the pressure, volume, temperature, cure, and visco-elastic method to characterize the polymer material used in the substrate, so that we can understand the impact of the cure and also the visco-elastic effect to the substrate warpage. This project also provides opportunity to software vendor or provider to develop a new material model to address the modeling gap we have today. And finally, we will conduct experiment on available test vehicle or sample to validate the model we have. So for today's presentation content, I will start with some introduction, followed by the implementation detail of the analysis model. The text section will be a result and a discussion we found in this project. And finally, I will sum up the presentation by conclusion. So before I start, I have some thought of the day. So is current modeling approach adequate for the industry? Can we include geometry variation in our model when we create the model? How can we add in the nonlinear and more complex material property into our model so that we can predict the warpage and some of the stress we want in our analysis? And how to account the residual stress of the assembly process we have encountered in the component? Is the modeling output we have today or the result we have today have taken into account all the variation and the incoming process variation, material, nonlinear geometry, and so on. So today, we are still working to refine the modeling method or step to account for all this multi-physics behavior in warpage modeling. On the introduction page, a practical warpage model should have covered the visco-elastic behavior of our polymer acid in the packaging. The time temperature dependent property for visco-elastic model were included with a two-step shift factor model of iNEMI and WLF function in this project. Some research found that the PVTC can influence the package dynamic warpage behavior, but this PVTC method is not widely available today. And so this project has an engaged PVTC model to estimate the cure shrinkage during the curing process so that it can be applied into our model to predict the package warpage. And the implementation for the modeling approach in this project, an organic package model was used in this project, together with the material model of our viscoelastic, time temperature dependent shift factor, and PVTC. Modeling software like Modex 3D and General FEA tool were considered in this project. We use that to simulate the package warpage based on the test rigor and the design we have. And then we carry on the stress analysis to compute the post-cure induced shrinkage, and followed by the time-dependent thermal exposure loading to capture the package dynamic warpage behavior. Yeah. The polymer material in this model is defined by viscoelastic model in the form of a Prony series with a time temperature dependent. The Prony series, or also known as the Maxwell model, is expressed in this equation here. And the model used to describe the shift factor WLF and iNEMI as shown by the equation in this page. And the next page here is the chart of the viscoelastic behavior for the polymer material we use in this project, where the property of a build-up and the solder resist firm is applied in this model here. So for the material property of the build-out and the solder resist firm, right, they are measured from 25 to 200 degrees C from a different time between 0.1 to 10 seconds. Yeah. And the material modulus reduce over time and temperature. And for the current kinetic polymer material property, current kinetic is used to study the current conversion of the polymer used in this project, especially on the build-up and the solder resist firm. The model used here is called combined model, and the equation can be expressed as shown here. With this, we are able to identify the cure state of the polymer based on the curing rate and the temperature. So from there, we try to identify the chemical shrinkage. The chemical shrinkage strength was applied to the model through PVTC. The equation is able to account for the chemical shrinkage during the curing process. And the model here, where we try to apply to predict the chemical strength, is known as the two-domain modified TAP. So next page is on the how we convert the PVTC data to chemical shrinkage. So from the measurement through the PVTC, we're able to get the specific volume changes against the different temperature for uncured and cured state. From the chart on the left, we are able to convert it into a more meaningful data, which is known as the chemical shrinkage. So we're able to get the chemical shrinkage for the solder resist and also the build-out material. With this information, we are able to apply the shrinkage value to the model to predict the warpage. And some further detail on the model we used in this study. The model is an organic package with a 37.5 by 37.5 mm size. There are 4 models here with a different layer count based on the lamination process. So basically, from sample 1 to 2, we have only like 2 metal layer, and the sample 3 and 4 we have a 4 metal layer laminate on the package. And the trace mapping method is used here to try to capture the unbalanced or unsymmetrical copper density on those metal layer. In general, the mesh size is 200 micron and with 3 elements across the thickness. Yeah. And the thermal expansion property for the copper is around like 70 ppm, and for the core is about like 9 ppm. For the solder resist and build out, right? Yeah, build out have a lower thermal expansion where it's between like 23 to 78, compared to solder resist is higher, where we use about 60 to 150, based on the data from a manufacturer. Okay. With this model, then we try to simulate the package warpage by using the transient copper temperature displacement analysis, where we assume the convective heat transfer is about like 20 watt per meter squared. Yep. So the initial temperature for each model is assumed here at 165 degrees C, and then the whole model is exposed to a 2-cycle temperature cycling to simulate the warpage of the model. So the temperature data is shown in the chart. Okay. So in this page, this is the explained data from Shrinkage for sample 1. The sample 1 is with a 2-layer copper and sandwiched by and with the core material only. So from here, it warps from concave to convex, which is from room temp to high temp. And on this page is the result, the experimental result for sample 2. Similar result and finding found for sample 2, where it consists concise with the sample 1. It warped from concave at room temp to convex at high temp. So it clearly showed that the 2 metal layer package used in this project will have the same behavior, where it warped from concave to convex. But even though the sample 2 have an additional layer of build-out material. Moving on to sample 3 result. So we can see some difference here. For sample 3, with 2 more metal layer, the new structure here have changed the package behavior, where it warped from convex at a low temperature to a concave shape at a high temperature. The changes here, is due to the imbalanced copper density and also the more layer added to the sample. So moving on to sample 4, with a same number count of metal layer, but with additional lamination of solder resist, right, it still behave similar as a sample 3. Yeah, where it warps from a convex at a low temperature to a concave at a high temperature. So in the following page, I will show you more on the magnitude of the warpage. Yep. So, and in the following page, right, is the comparison between the modeling and the experiment data also. So let me start with the sample 1 and sample 2 result. For the modeling result, we are able to predict the 2-layer substrate warp from concave to convex. Similar behavior as what we've seen in the experiment data. If you look at the sample 1, the sample 1 warpage predicted is a match well with experiment result. It's almost sync with the experiment data. And for sample 2, we have two modeling results. One is with cure and one is without the cure. And we found that the modeling with a cure is more matched to the experiment data compared to the no cure. And it comes to my next page is on the modeling result for sample 3 and sample 4.
Sure.
So in here, you can see that, yeah, with an additional layer to the sample 3 and sample 4, right, the warpage behavior of these two samples is totally in the opposite direction compared to the sample 1 and sample 2. Yeah. So sample 3 and 4, it warp from convex at low temperature to concave at high temp. For sample 3, we see small changes in the warpage with cure model. And the cure model is getting better result compared to the no cure. Similar finding apply to sample 4 also, where the cure model improved the warpage prediction, where it's closer to the experiment data, but we still find a gap here compared to the experiment. Yeah, what we see here is about like more than 50 micron gap between the experiment and the modeling here. And if you compare to the model with cure and no cure, we can clearly see that there's a 50 micron delta changes. And some of the explanation I have for the difference between the experiment and the model with cure is the cure shrinkage due to the light during the solder resist cure, right, is not considered in the simulation. So what we consider here is only during the cure due to the curing due to the temperature only. Yeah. And with this, it come to my summary or conclusion of this project. So the use of our organic package in this project have demonstrated the impact of our transient thermal structure analysis coupled with the effect of our visco-elastic and cure model implementation in the warpage modeling. The cure shrinkage should not be neglected as the predicted value can be highly influenced by the conversion of the polymer. And from this project, right, not only the more material, but polymer in substrate should also consider. Yeah, we should include the cure shrinkage in the polymer too, as it will affect the incoming substrate, as what we have seen in this project. So not only the more material, the solder resist and the build material we have in the substrate, right, should also consider the shrinkage. And the last point I have is the logical step for this industry project is to validate the effect seen on the viscoelastic behavior and the cure shrinkage impact. And with this is what I have for today sharing.
Okay, thank you, Kang Yu, for the
Yep.
briefing of the results. I see there are some questions in the chat. Kang Yu, if you also can open the chat. First question we have is from Samko. He asked what cure condition we used in this work.
Okay, so for the solder resist, right, is cure at I think it's cure around like 160 to 180 degrees C for about like 60 minutes before it's cool down to room temp.
Okay. I think everyone, if you have any questions, you also can speak out. We will first go through those questions in the chat. If you want to talk, you need to unmute yourself. Okay. The question from Jack Chen is asking if the bake can reduce the warpage.
Yeah, in this study we didn't consider the moisture, but if the substrate or the package is have been exposed to the moisture or the environment, right? Yes, the answer is yes. The bag can reduce the warpage.
Okay, the next question is, do you have any suggestions on how to practically measure the cure shrinkage of the polymer in the substrate?
Okay. Yeah, so far we still try to fine tune and try to determine the best method to measure the cure shrinkage of the polymer in the substrate. And current method is we are getting the help from Motor 3D to measure the shrinkage, and we still still trying to fine tune the methodology to get the shrinkage value.
I don't know if we have anyone from Modex 3D can add any comment. If you okay, let's move on first. Okay, how did you account for the difference in the copper line density?
Yep. So as shown in this as shown in this page 13, right? We try to use the trace mapping method, where we try to assign the copper density or the copper property to the element in the model, right? Based on the design. So we try to map the element from the model based on the design to assign the copper density to the model. So for example here, if you found that the at this certain location, right, based on the design coordinate is a copper material, right, then we will try to assign those elements with a copper.
Okay. The next question is about the structure you show in the symmetrical top to bottom. What breaks the symmetry to determine the direction of the warpage?
Oh, okay. So in this cartoon is showing it's showing symmetrical, but actually in the design, in the actual pattern on the sample, right, it's not symmetrical. There are the copper distribution on the layer actually is is imbalanced and non-symmetrical. That's why the imbalanced copper, right, cause the warpage, cause the overall substrate to warp in a different direction. Okay. Yeah. In short, actually the the structure we have in the substrate is not symmetrical.
Okay, then the next question is, what's the purpose of transient thermal simulation in the analysis?
Okay. The objective of using the transient thermal simulation, right, is because we want to determine the curing effect, the cure state based on the temperature changes in the model. So we want to know what is the curing percentage based on the temperature distribution in the model, so that we can accurately capture the cure state. From there, we can apply the right shrinkage value to the model to predict the effect of the shrinkage. And also take into account the visco-elastic effect of the material property.
Okay, I see Andrew Tai raised the hand. You want to ask a question?
Yes, please. Can you hear me okay?
Yes.
Okay. Yeah, I want to ask, related to this question about the thermal analysis. So do you account for the temperature distribution across the thickness of the PCB as well?
Yes.
We do that.
Because yeah, we do that. Because in the model here, right, we apply the this heat transfer coefficient on all the surface, so that the temperature is transferred from the outer surface to the inner part of the substrate.
Yeah. Okay. Then you mentioned that your initial temperature is 165 degrees C. Is that correct?
Yep.
But your okay, so the temperature profile is what you have shown in this diagram, right? Start at 165, then it goes down to 25, and so on, right?
Yes. It went through a 2-cycle reflow to simulate the warpage changes according to this temperature profile.
Okay. Just to follow up my earlier question about how you account for the difference in the copper line density, right? In the various layers. So all the elements are 100% copper or 100% what do you call it, polymer, right? Do you have any element which are like partly copper and partly polymer?
No, because we try to use a fine mesh here, so that you're able to capture all the design distribution based on copper or dielectric only.
But I guess there may be some elements, of course, maybe 90% copper and 10% polymer. I guess you just take it as 100% copper, is it right?
Correct. Yes.
Okay. And was this done manually or done by the computer?
It was done by the software.
Okay.
And yeah, this software ANSYS have this capability to read in the design information and assign those info to the model.
Okay, thank you.
We have another question in the chat asking, can you give a detailed description to consider the cure shrinkage in the modeling?
Shrinkage model. Okay. Okay. Let me put it this way. Okay. Yep. So at the start of the modeling analysis, right? So we're able to we assume that the sample is about 100% cure. Then with that, we are able to based on the conversion here, we are able to know what is the shrinkage value, like about 2.5% and so on. And this shrinkage value can be converted into some sort like a strength, and it's applied to the model at the start of the analysis. So before we go through the thermal cycle to simulate the thermal strength, right? The shrinkage value in the cure strength is already applied to the model already. So it will the strength will be carry around the whole process here to sum up together with the thermal strength. Yeah, to compute the total strength to the model, and from there we calculate the displacement. Do I answer your question? Yeah.
Sorry, Andrew here. Can I just follow up with that question?
Yeah, sure.
Yeah. So your curing is so you have some results with cure and without cure, right?
Yes.
So the with cure means that the cure is taken care of in the right at the beginning of the whole process, right?
Yes.
Okay. So so during the site, okay. So your assumption is 100% cure already at the start of the process. So subsequently, there's no more curing, right?
Yep. Subsequently, is no more curing. We assume that the whole substrate had been cured, and then the cure have created some cure strength to the model already.
Okay. Is this a good assumption, you think?
Yeah. So far the example here, the test we have we have here is already like been cure for 60 minutes, about like an hour already. So after 1 hour, I think all the polymer should be fully cured.
Okay. Can I just ask one more question?
Yeah, sure. Go ahead.
Okay. So across the thickness, you say you have you use three elements to model the thickness of the PCB, right?
Yes.
And how thick is your PCB?
The total thickness here is about 400 micron.
400 microns, huh? So you divide by 3 is about.
Yeah. The core thickness alone is about like 200 micron already, and then the copper thickness is about 15 micron.
Okay, got it. Thank you.
Yep.
Hey, Kang Yu, it's 3 elements across a single layer, right?
Yes.
Yeah.
Yeah, it's a single layer. I mean, yeah.
So each thickness you have each material thickness you have 3 elements across that. So at least, yeah. Okay.
Okay. There are 2 more questions come up. First, for the practical purpose, do you have plan someday in the future to come up a material combination that BGA packages can be produced to prevent head-on payload defects in BGAs? So do you mean consider both the package and the PCB?
Both the package and PCB in the model.
Yeah.
Yep. I think the answer is yes. Yeah. In future, if we have this capability and opportunity, right, then yeah, we can apply this methodology to the whole setup with a package and the PCB board. Yeah.
The next question, will there be a significant difference in warpage if uniform temperature is assumed at each stage in the reflow process, instead of using non-uniform temperature? For from thermal analysis.
Okay. Yeah, for this question, right, it will mainly depend on how thick the package you have. So if your package is thicker, right, then we will expect that there's a temperature variation between the top and bottom surface. But if your package is thin, it's a very thin package, right, then it should not have a big delta between the top and surface, and we will not see any big changes in the warpage if the package is thin. So this is mainly depend on the thinness you have. Yeah.
Okay, the next question is, have you assessed the impact of visco-elastic properties on the warpage results?
So in here, do you mean that have we compared the visco-elastic property with only the elastic property? I think we have done that before by comparing the visco-elastic and elastic property, but in here we didn't show that result. Yeah.
Okay. Are there any other questions?
Yes, this Andrew here, I have a question. Okay. Yeah, so you mentioned towards the end that there's a difference between the model with cure and the experimental results, and you attribute this to the additional shrinkage from the lights, right? Exposure to light, which was not taken into account.
Yep.
Will you be able to assess what kind of shrinkage could be attributed to the light, and whether this will actually make the fit with experiment better?
So far, I don't have any idea yet, and this is new to me also, because we just found that from the substrate supplier that when they cure the solder research, right, actually they have a two-step cure. The first one, they cure it with a temperature reform, and then followed by the light by the light cure. So yeah, this will be our next project also to be considered, like to identify the cure shrinkage from the light.
So you mean the curing with temperature is going through a temperature reflow? So it's not just storing at a high temperature for minimum, let's say 60 minutes, right, as you mentioned.
Yeah, it's actually it's not temperature reform. It's the temperature heating. Yeah.
Temperature in the oven. Okay.
Yeah, temperature in the oven.
Temperature.
Yes.
Okay. Right. Thank you.
Yeah, and somehow we found that they have also cured it again with the light, with the UV light. And so far, yeah, we still haven't look into it on how to get the shrinkage from that. Yeah.
Do you intend to include moisture effects in future? Because once moisture diffuse into the but moisture diffusion is a very slow process. Yeah. So yeah, it depends on if you are doing the experiment, doing the measurement immediately after the what is done during the whole process flow, right? So
yep.
So if you start off with a dry, everything dry, then there should be no moisture issue.
Yes.
Yeah,
And
moisture
also
is only
depend
coming
on
later on. Once you expose it to moisture.
Yeah. Hey, Kang Yu, may I add on?
Yeah. Yes. Please go ahead. Yeah.
Hey, Andrew, Wakehead here. Also working on another project with iNEMI on this moisture swelling of polymer. So we are currently putting the plan together, and we plan to launch this project beginning of next year. So we are thinking of taking the measurements of polymer expansion to even higher temperature, like what compared to whatever existing metrology that we can get from off the shelf. So yeah, stay tuned. I mean, we try to combine all these effects together, but individually, those materials need to be carefully characterized in order to incorporate this multi-physics together.
Yeah. Yeah, but let's say if you have moisture, so precondition the moisture in the package, right? Then during the temperature cycling process, there could be some moisture, significant moisture diffusion out of the package that will affect the warpage as well. So it's quite a complicated process.
Yes.
Okay, there is another question come up in the chat. In the modeling, sample 3 and 4 has a higher warpage than sample 1 and 2. More built-up layer make warpage worse. Is this contribute more by the copper imbalance or polymer visco-elasticity from the modeling?
Okay. Yeah, for this, I think that is more from the polymer visco-elastic, because as you know, when we have added more copper layer to the structure, right, it will become stiffer. But when we have additional polymer, right, due to the high CTE, the high CTE value we have in the solder resist, then yeah, it will make the overall warpage higher. So as what I have shared in page 13, right, when we the solder resist is having like a larger thermal expansion compared to the core and also the build material, so that it will influence the overall warpage to become higher.
Sorry, follow this question. So in other words, if we play around more on the copper, that will make those warpage more relaxed in the design point of view. Based on this modeling, that probably the good powerful on this modeling can give some designers some idea. Thank you for this prediction.
Okay.
Are there any more questions or comments?
Yeah, this is Andrew again. Can I ask another question?
Yep, sure.
Go ahead.
Yeah. So the so let me see. I understand your structure. You have a core of the PCB material core, right?
Yep.
Then on both sides you have build-up layers. Is that right?
Yep.
So you say your core is modeled by 3 layers of elements. Then your build-up layers are modeled by thinner layers, I suppose. Is that right?
No, also with three element across the thickness for each layer.
For which layer? The build-up layer?
Yeah, the build-out and the copper layer, right? They are with three element.
Three element divided by three element thicknesses.
No, okay. The whole thickness divided by three element.
Yeah, I understand. But let me see. You say your thickness of the copper layer is what? 15 micron.
15 micron. Yeah.
And then the dielectric layer will be
25.
25 micron. So I guess you would have a layer of dielectric elements which are 25 micron, then a layer of copper which are 15 micron, and so on, right?
Yes, a layer of copper with 15 micron, and in the copper layer, right? Then I have 3 element. The 3 element is basically like 5 micron.
Oh, okay. 3 elements
Ah.
across the copper layer. Okay.
Yes.
And then the
yeah.
dielectric layer, which
Same.
is 25 micron thick, you have
and-
3 layers of that.
Yeah, I have like a 3 layer of element, like about like 8 micron
Okay.
thickness.
So, okay. So in this layers, then let's say you take copper, for example, right? You have an element which is 5 micron thick, and then 200 micron length and width, right?
Yes.
So this is a very thin kind of element, right? So what kind of element type do you use?
It's a quadratic element.
Yeah, but what kind of element type? Is it the solid element? Is it the normal 3D
It's a
solid
solid
element?
element. Solid element.
Okay.
Yeah,
Because you know for thin elements like this, right? I understand that there is a special kind of element which seems to be more accurate. What's the name for it? I can't remember. But
Do you mean
in the
like
sense,
hybrid type element for that?
yeah, I think Abacus calls it differently. I think ANSYS calls it differently also, I think. But basically, it accounts for the fact that it's very thin. I think it allows for some strain variation or something like across the thickness.
Yep.
Something like that. But anyway, you're just using normal solid elements.
Yes. Yeah.
Okay. All right.
In this project, we just use the normal solid element, similar to the element type we have in Model 3D also. Yeah, to try to simulate the warpage.
I think you may want to try to use this special kind of element, which is especially for thin. Okay, I remember now. It's instead of treating the plate, right? It's kind of
something like that.
Yeah, it's kind of a plate element, but it allows for variation in strain across the thickness, and it seems to lead to cheaper computation time. I think in terms of accuracy, it may not improve that much, but it will save a lot on computation time compared to the solid element. I think that's correct.
Yeah.
Yep.
Yeah. We also need to use the elements that is compatible to thermal heat transfer analysis as well. So yeah, as long as maybe something to try out in the future. Thank you.
Yeah.
Okay. Yep. Okay. Yeah. Do we have any more questions? Yeah.
No, I think we have all the questions covered. So I would take the chance to thank you all for joining the webinar. So this is a continuous project. Today we just reported the work that we have done in phase 5. There are some opportunities for future work, and I see a number of you has good experience and knowledge in this field. We would welcome you to get involved when we plan the next project. Hopefully, we can pick the right factors or the right directions or even interested packages to work on for the future. So we will start the discussion of the next project after the New Year holiday. If you are interested to get involved, you can contact me. We will share the presentation slides after the session. Tomorrow we will have a same session just for different the people in different geography to join. so we can continue the communication. If you come up with further questions, just let us know. With that, I wonder, Vicky, you want to give any further comments?
Yeah, I mean, I want to thank the team, right, to put this thing together. I mean, there's a lot of back and forth discussions about the material properties and ensuring all the boundary condition is correct, and then considering factors that is beyond what we know historically on what affects the package warpage, and having the collaboration with suppliers and a different kind of modeling softwares that allow us to see things more broadly and account for things that we neglected in certain cases in modeling this package warpage, right? It has been a challenge for sure. Moving forward with heterogeneous package, and like Andrew said, right, the moisture plays a big role. The layer count increase, the package size increase. Yeah, I mean, and it's not cheap to build a heterogeneous package as well. So having modeling capability to predict this well is very critical, because it takes away the risk, right, when you invest in certain packaging technology. So having the team looking at the visco-elasticity, the curing influence for the package warpage, that elevates the awareness of what it takes to run these predictions. And for sure, it's not something that we press a button and then we get the answer. We need to get all the collaterals, the material properties correct to make this work. And like Ellie mentioned, right, this is a continuous effort. We have been pulling this team together, right, across the industry. If anyone interested, please contact Haley, and from there we'll discuss the next phase and then continue build not only the work but also the leaderships among the technical community. Right? So in that way, collectively we put the knowledge together for the industry. I think hopefully that summarizes, Haley. Thank you for the team effort here.
Okay, thank you, Vicky. I think there may be some further questions beyond this project. There is a question about the HIP heading payload inspection. In fact, we have other project. It's a finished project on the AXI AOI capability on the head-on payload, heading payload inspection. Maybe I can share with you later about what we have done there for your reference. Okay. Okay. I think with that, we will close today's session. So thank you all for joining. Thank you, Kanyu, Vicky, and the team. Okay.
Yeah,
have
thank you,
a
Haley.
good day, good evening. Bye-bye.
Thank you.
Okay,
bye-bye.
Bye-bye. Thank you.
Bye.